Hello, I am Riwaj. Welcome to the poster on faster Myelin water mapping by joint reconstruction and estimation from highly undersampled 3D multi-screen echo acquisitions. Myelin water fraction can be used as biomarker for myelin content in central nervous system. Among various sequences to measure myelin water fraction, multi-spin echo sequence is considered as the gold standard. However, its clinical application is limited due to its long acquisition time. In this work, we address this problem. Acquisitions with multiple contrast images, such as multiple spin echo, can be accelerated using the redundancy in the contrast dimension. This has been applied for other parameters such as T1, T2, and T2 star mapping. In this work, we want to apply this for Myelin water fraction. Unlike other parameters, Myelin water fraction requires multi-exponential fitting, which often needs constraints such as non-negatively square. This equation shows signal originating from each voxel, which consists of number of T2 components. Fitting this model to measured magnitude images requires non-negatively square constraint. This can be challenging to do within a joint reconstruction estimation framework. The models are generally based on magnitude images, while these techniques work on complex data. Application of such constraint also makes the problem computationally complex. Hence, in this work, we propose using subspace constraint reconstruction. In this type of reconstruction, we generate linear subspace that spans the model. Then, we constrain the reconstruction to fit this subspace. To create the subspace, we use the derivatives of the signal with respect to each T2 component, decompose it using singular value decomposition. Then, the obtained components is considered as subspace. This is then used to constrain the reconstruction. So, looking at the overall picture, we do a fast undersampled scan, use the proposed technique to reconstruct contrast images, then you use the conventional multi-exponential fitting to get the Myelin water fraction maps. For verification, we performed a Monte Carlo simulation using the ground truth shown here. We use the multi-exponential model to generate contrast images. The images are then multiplied by coefficients into maps and Fourier transformed to get K-space. The K-space is undersampled using pseudo-random undersampling pattern. Finally, a complex Gaussian noise is added. We repeat this for many acceleration factors and SNR cases. The reconstruction was performed using three different number of subspace components. Generally, low SNR cases are reconstructed better with lower number of subspace components. The graph shows the best results among the three subspace components used during the reconstruction. Further verification was done using retrospective undersampling with acceleration factor of 6. We can see the result on the right while the ground truth is on the left. Please pause the video to look at the results. Therefore, we conclude that subspace constrained reconstruction can be used to exploit the redundancy in contrast dimension without explicitly using a model. Scan time can be reduced by undersampling and using subspace constraint reconstruction. Further validation using a prospectively undersampled scan is ongoing. Thank you for your attention. If you have any questions, feel free to contact us.